Namaskar students, in the previous video we have discussed the statement of Rolle's theorem and the geometrical interpretation of it. In today's video we shall see a few examples related to Rolle's theorem and finally we shall try to deduce some observations from the Rolle's theorem. So let us start today's video. Before moving on to the problem, let us have a brief recap of the statement of Rolle's theorem. So there were two parts of this Rolle's theorem, the hypothesis part and the final conclusion, that is the result part. Now see, what was the hypothesis part? We had considered that f is a function, real valued function from closed interval ab to r, such that three conditions should hold. First condition, f should be continuous in ab, closed interval ab. The derivative should exist at all points in between a and b, that is the open interval ab, and the last part, that is the functional value at the boundary points should be equal, that is fa should be equal to fb. If all these three conditions hold, then we can tell that we can find a c in between ab such that the derivative of the function at the point c will be equal to 0. Now see, whenever a problem will be given in this regard, it will be given in such a way such that you have to verify Rolle's theorem. So how will you verify Rolle's theorem? What is the meaning of verification? See, verification means if a function, whatever function it is given, fits into the hypothesis, then the result will hold true. We have to verify this. That is, firstly, given any problem, any function, we have to test whether these three conditions hold true or not. If these three conditions hold true for that function, then our duty is to find out a point C in between AB such that this equation holds. That is, f dash C will be equal to 0. That is, the derivative of the function at the point C will be equal to 0. We have to find out that C. Our work is to find out that C, but at first, provided these three conditions hold. So I am telling once again, given any function as a problem, our work is to first find out that these three conditions hold or not. That is, the function is continuous or not, the function's derivative exists or not, and at the boundary points the functional values are equal or not. If these three conditions hold, then our final work is to find out this point C. Anyhow, we have to find out this point C so that the derivative of the function at that point becomes equal to 0. This will be our mode of work given any problem related to Rolle's theorem. So let us move on to the problem section. So this is our first problem. We have to verify the Rolle's theorem for the function fx equal to 1 minus x square in the closed interval -1, 1. Now let us fit this problem into the hypothesis part. Let us try to relate what is given. See, here the function is 1 minus x square and AB is -1 plus 1. So as I told, what you have to do, we have to first test whether these three conditions hold true or not. Once again I am telling, given any problem like this, first part of the problem is to test whether these three conditions hold or not. If we can find that these three conditions hold true, then we have to find out a point C such that f dash C equal to 0. Firstly, let us test these three conditions. First condition is f should be continuous in AB. See, what is the meaning of continuity? Continuity means anyhow you will not find any discontinuous point of the function in between the interval AB. Here the interval is -1 plus 1. Now the simplest way to understand that this continuity part is that you have to test whether at any point in between -1 and +1, including the boundary points, this function becomes undefined or not. Okay. See, you can put any value of x starting from -1 to +1, you will find a value of fx. You can find a value of fx. See, here f start with -1, f of -1. So it is -1 minus -1 whole square, that is 0. Start with any point after -1, say half. 1 minus half square, you can get a value. In any number that comes between -1 and +1, you put that number value in place of x over here, you can find a value of fx. This shows that the function can produce any real value between -1 and +1. Thus, the function has no discontinuity. Hence, the first part, if to be continuous in AB, that holds true. So, how will you write that? You will have to write like this. Since fx gives real values for all points in -1, 1, we can tell fx is continuous in -1, 1. So the first part, if to be continuous in between a and b, that holds true. Now for the next part, the derivative one, see, if this is the function, then what is f dash x minus 2x? Now whether f dash x exists in between open interval -1 +1, we have to see the same thing, that f dash x is producing all values between -1 and +1 or not, real values or not. If at all f dash x becomes undefined at any points between -1 and +1, then we can tell that f dash x does not exist at all points. Here see, luckily f dash x is equal to -2x. You put any value of x between -1 and +1, see, you can get a real value. So there is no point between -1 and +1 such that you can put that point in place of x and get an undefined case. So there exists no such point. Hence, you can tell that f dash x exists at all points in open interval -1 +1. For continuity case, it was closed interval. For derivative case, it should be open interval. See, I'll just give you a just reverse example. If at all there would have been a function such that you are getting f dash x equal to some -1 by x squared type, for example, then see, this function is not defined for all points between -1 and +1, because there exists a point 0 between -1 and +1, and if you put the value of 0 in place of x, this becomes undefined. So if the derivative would have been -1 by x square, say, then we couldn't have told that the derivative exists at all points between -1 and +1, because there now comes a point 0 which makes the derivative undefined. But in this case, since the derivative is -2x, there is no point between -1 and +1, which if you put in place of x, the function becomes undefined. So here f dash exists at all points in between -1 and +1, and hence the second point also holds true. Now come to the last point. See, for the last point, the functional value at the boundary points should be equal. Here the boundary points are -1 and +1. So what is f of -1? 1 minus -1 whole square, that is 0. What is f of 1? 1 minus 1 square, that is 0. Hence you can tell that, therefore f of -1 equal to f of 1. That is, the third point also holds true. So after showing all these points, 3 points to hold true for this function, our work is now to find out a value c in between a and b, here -1 and +1, such that the derivative of the function at that point becomes equal to 0. See, what is f dash that we have got over here? We have got f dash as minus x square, sorry, minus 2x. Now for the derivative f dash x to be equal to 0, see, minus 2x should be equal to 0 or x should be equal to 0. See, this point 0, if you put in place of x, the derivative becomes equal to 0. We can safely tell, therefore, f dash 0 equal to 0. Now see, let us test whether this point 0 lies between our given interval or not, because what we have to find, we have to find a point c which is between the interval ab, such that the derivative at that point becomes equal to 0. Obviously here, see, the point 0 lies between -1 and +1. Here 0 lies between -1 and +1. We can safely tell that. And the derivative at that point 0 is also 0. Hence we can conclude that we have found a point c which is 0 over here, such that derivative of the function at that point is becoming equal to 0. This was nothing but the conclusion of Rolle's theorem. How did we conclude? We have concluded because we proved these 3 conditions hold true for this function. After these 3 conditions holding true, we found a point c, here the point is 0, such that derivative of the function at that point becomes equal to 0. Hence, see, all the hypothesis and the result part becomes verified. That is, since these 3 conditions are holding true, we can find a point for that the derivative of that point becomes equal to 0. Hence, Rolle's theorem is verified. I'll just conclude once again and try to understand, students, that verification of Rolle's theorem is very easy. You just have to understand the statement of Rolle's theorem. You have to just show that these 3 conditions hold true, and after these 3 conditions holding true, you have to find out, anyhow you have to find out a point c in between the given interval, such that the derivative of the function at that point becomes equal to 0. This is our only work for this class of problems. Now if all the conditions of Rolle's theorem are satisfied, then you can find out a value c such that the derivative of the function at that point becomes equal to 0. Now what happens if any one of these 3 conditions, or all 3 of the conditions, does not hold true? Then what? In the next 2 problems, we shall try to demonstrate these type of cases where some or all of the condition of Rolle's theorem are not holding true. This is one example in which you will find that one or multiple of these conditions do not hold true. Then what to do? See, for solving this type of problem, let us try to understand what function is given over here. The function is mod x. What is the mod x function? See, mod x function means whatever input you give, the output will always be non-negative. Hence, the function is defined like this: mod x equal to x when x is greater than 0, mod x is 0 when x is equal to 0, and mod x is minus x when x is less than 0. How? See, what is mod of 4? When x is 4, 4 means it falls under which category? It is greater than 0. So the first category tells that whatever you put over here in place of x, the output will be that only. If it is mod x, the output will be x. So if it is mod 4, the output will be 4 only. Mod of 0, if x is 0, then the output will be 0. Suppose it is negative. say minus 2. So if x is negative minus 2, it falls under the third category. It tells that if x is negative, the output will be minus of x. Here x is minus 2. So the output will be minus of x. That is, here x is minus 2, so it will be minus of x. That is minus of minus 2 plus 2. See, this is actually the dissection or anatomy of the function mod x. Now, to understand the function completely, let us draw the graph of this function. What is the graph of this function? This is x-axis and suppose this is y-axis. Now, for 0, the function is 0. For greater than 0, it is x. X means this line. X equal to x means this line. And for less than 0, it is negative of x. So it is this line. Okay. So mod x function is like this. This is the mod x function. The portion for x greater than 0, the portion for x less than 0, and this is at the point x equal to 0. See, unlike the function stated in the previous problem, here the function is not a very straightforward function. It is a function which is broken up into 3 parts. For x greater than 0, for x equal to 0, for x less than 0. And maybe the function has some discrepancy, maybe. We do not know that. Maybe the function has some discrepancy at the point 0 because the function is probably breaking itself at the point x equal to 0. See, so let us test whether the function is continuous at the point x equal to 0 or not. Because for the function more than 0, greater than 0, mod x equal to x, the function is equal to x. Here we can tell the function, here the function is mod x. For x greater than 0, it is straightforward equal to x. There is no undefinedness in x for all values of x. For the function less than 0, it is minus x. There is no undefinedness. Okay. For the point 0 also there is no undefinedness. But let us, just to be sure, test whether the function actually has some discrepancy at the point x equal to 0 or not. Just to test the continuity. How to test? See. X tends to 0 plus fx and limit x tends to 0 minus fx. We have to find out these two values, that is the right hand limit at the point x equal to 0 and the left hand limit at the point x equal to 0. These two are becoming equal or not. If these two are equal, no problem. The function is continuous at x equal to 0. What is the right hand limit? Right hand limit means that x is approaching 0 from the right hand side of 0. See, if this is the x-axis and this is the point 0 and this is the x-axis, x can approach 0 either from this side or from this side. If x is approaching 0 from the right hand side, we tell x tends to 0 plus. If x is approaching slowly approaching 0 from the left hand side, we tell that x tends to 0 minus. Here if you remember, the function is like this. At 0, mod x function. See, for x tends to 0 plus, that is x has values over in this portion, x is tending from the right hand side of 0. So x is positive. If x is positive, what is the value of fx? X. X is positive, fx is x. If the value of fx is x, we put the value of 0 over here. What do you get? So limit x tends to 0, x 0 plus x. So that is 0. The limit is 0. Here also, when you are telling limit x tends to 0 minus, that means from the left hand side of 0. Left hand side of 0 means x is negative. If x is negative, what we have? X has, fx has minus x. For the negative part, fx is minus x. So x tends to 0 plus. Put value 0 over here. You get same thing. Minus of 0 is 0 only. So here see, our thought of discrepancy, maybe there was some discrepancy at the point 0, is actually wrong. See why? Because the limit, left hand limit and the right hand limit, both left hand limit and right hand limit, both at the point 0 are becoming equal. Hence, we can safely tell that function has no discrepancy at the point 0. The function is smoothly, equally continuous at the point x equal to 0. So the first part, f to be continuous in AB holds true. Here the function becomes continuous in between -1 and +1. Now we move on to the next condition, that the derivative, whether it exists in between a and b, that is -1 and +1 or not. See here also, if you do a derivative over here, it has three parts. F dash x, this roughly becomes equal to derivative of x is 1, derivative of minus x is -1, that is okay with that. But here also at the point 0, there is some ambiguity. There is some thought of discrepancy. Let us test whether the derivative exists at the point 0 or not. Same thing, we have to test whether the right hand derivative and left hand derivative are becoming equal or not. As you all remember, you can recall that the right hand derivative f dash 0 plus, how to define that? Limit x tends to 0 plus fx minus f0 by x minus 0. See, x tends to 0 plus. 0 plus means from the right hand side of 0. If this is 0, x is tending from the right hand side of 0. Right hand side of 0 means x is positive. If x is positive, which value to take among these three? X positive, that is x. So for here, we have to consider limit x tends to 0 plus fx for this x. What is f of 0? At the point 0, at the point 0 it is 0. So x minus 0 divided by x minus 0, cancel out, that is equal to 1. Now let us move on to the left hand limit, f dash 0 minus, that is limit x tends to 0 minus fx minus f0 by x minus 0. 0 minus means if 0, then from the left hand side of 0, that is x is negative. If x is negative, which value to take among these three? The last one, x is negative, that is minus x. So here it becomes limit x tends to 0 minus fx will be negative, that is minus x minus 0 by x minus 0. If you cancel it out, minus x by x, that is equal to minus 1. Here see, unlike continuity testing, the right hand derivative and the left hand derivative, the values are not equal. If the values are not equal, we cannot tell that the derivative of the function exists at the point x equal to 0. For the derivative to exist, the right hand derivative and the left hand derivative must exist and should be equal. Here they are not equal. Thus, the second test part, whether f dash x exists at all points in between a and b, is not holding true. We are getting a point over here 0 at which the derivative is not existing. Hence, the second part is not holding true. As I told, if any of these three conditions do not hold true, it is safe to not proceed further. We can tell we cannot verify the Rolle's theorem because one of these three conditions is not holding true. Just for the sake of understanding, let us see whether the derivative, we can find a derivative. The conditions are not holding, one of the conditions is not holding. It's okay if one of the condition is not holding. But can you find a C such that the derivative is equal to 0? See, in the previous video, I have told you the geometrical interpretation, that is, when will the derivative at a point become equal to 0? At that point where the tangent is becoming parallel to the x-axis. If you can find a tangent at a point upon the function such that the tangent is becoming parallel to the x-axis, then the derivative at that point becomes equal to 0. Here if you observe the function mod x, the function is like this. See here in the function you cannot find any point where you can draw a tangent and tell that that tangent is becoming parallel to the x-axis. Hence we can tell you cannot find any c in between a and b, that is -1 and +1, such that the derivative of the function at that point becomes equal to 0. Now this conclusion we can tell because one of the conditions are not holding true. My next question is, if all these conditions hold true, then the result also hold true, that we have seen in the first example. In this example we are seeing that one of these three conditions is not holding true, hence you are not getting a point c such that the derivative is becoming equal to 0. My question is that even if these three conditions or any of these three conditions do not hold true, still can you find a c for which the derivative becomes equal to 0? Let us try to find out from the next example. Consider this problem. Here we have to test the Rolle's theorem for the function fx equal to 1 by x plus 1 by 2 minus x in the interval 0 to. Firstly, we have to test whether these three conditions hold true or not. See, over here at the boundary points 0 and 2, what happens if you put f0 over here? 1 by 0 plus 1 by 2 minus 0. This is undefined. Anything divided by 0 is undefined. So the function is becoming discontinuous at 0. Similarly, here the function at 2 also. See, what is f of 2? 1 by 2 plus 1 by 2 minus 2, that is 0. Again 1 by 0. So at both the boundary points, the function is becoming undefined, that is discontinuous. Hence the first condition of continuity does not hold true over here. Similarly, the last condition also, the functional value should be equal, and equal means what? Equal means you have to get a finite value. Here at the boundary points you are not getting a finite value, it is becoming undefined. So the first condition and third condition is not holding true over here. If the condition is not holding true, in the previous example we have seen that we did not get a point such that the derivative is becoming equal to 0 at that point. Let us see in this problem whether we can find a point where the functional value, the derivative of the function is becoming equal to 0 or not. Okay. See, what is the derivative of this function f dash x? Minus 1 by x square plus 1 by, you can do the derivative by yourself, I am doing a step jump, plus 1 by 2 minus x whole square. Okay. See, f of 1 over here, if you put 1 in place of x, what happens? Minus 1 by 1 square plus 1 by 2 minus 1 whole square, that is equal to 0. Minus 1 by 1 square is 1 plus 1 by 2 minus 1 whole square, that is 1. So minus 1 plus 1, 0. So you are getting a point, which when put in place of x in the derivative is becoming equal to 0. Let us see where this point lies. See here, this point 1 lies between 0 and 2. So actually you are getting a point between 0 and 2 where the derivative is becoming equal to 0. Even if more than one, or say one of these conditions are not holding true, we have seen that in this problem one of these conditions, two of the conditions are not holding true, still you are finding a value c such that the derivative is becoming equal to 0. So what is happening over here? What is the observation, important observation that we can deduce from the last three examples including this one? See, recollect what we have stated in Rolle's theorem. What was the statement of Rolle's theorem? The statement told that if these three conditions hold true, then the result will hold true. It does not tell anything that if this condition do not hold true, what will be the result. Hence, this theorem is only a necessary condition theorem, not a sufficient condition theorem. Necessary condition means for holding the result to be true, these three conditions are necessary. Necessary. That is, if these three conditions hold true, then obviously and definitely you can get a point C such that the derivative at C becomes equal to 0. This theorem tells nothing about if any of the conditions are violated. It does not tell that if either of these three conditions are violated, you cannot get a C. You can get a C, maybe you cannot get a C. See, in the previous example, just the example before this one, the conditions were violated. Okay, the derivative, we do not get the derivative. And we have seen that this result is also not holding true. We are not getting any point C for which the derivative is equal to 0 for the mod x example. Here we are seeing a different thing. That is, the conditions are not holding true, but still we are getting a point C for which the derivative is becoming equal to 0. Here the point is 1. At 1, the derivative is becoming equal to 0. Hence, now it is high time to understand the Rolle's theorem properly. Rolle's theorem tells only the necessary part. If a problem is given to you and you are told to verify Rolle's theorem, your work is simply to verify these three conditions. If these three conditions hold true, fine. Then move on to the step where you are finding a point C such that the derivative is equal to 0. If any of these three conditions are not holding true, your job is done. You can safely tell, since these three conditions or any of these three conditions are not holding true, I cannot verify Rolle's theorem, because if the conditions are not holding true, you cannot definitely tell that you will not get a point C like this. You cannot definitely tell this also that, okay, still you can get point C such that the derivative is equal to 0. It's only that when these three conditions hold true, then you can move on to the verification part. Okay. So this was the observation that we made from today's video. That is, the Rolle's theorem is only a necessary condition theorem. It is not a sufficient condition theorem. So my dear students, this is all what we had for today's video. I hope these three examples will make you feel better to understand the Rolle's theorem, and to also to understand that the Rolle's theorem is a necessary condition only, not a sufficient condition. If you have liked today's video, share this video with your friends, subscribe to my channel and follow my page. Till then, goodbye.